There's a man being attacked by a snake in the front row. Oh my God. Okay, shh, 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 shh. Now, did everyone move? Who didn't move? I'm moving. You're moving, good man. You didn't move. I made you move by putting your hand up. I tricked you. You pump blood to that side of the brain, so you'll be very, whatever that side of the brain does now. Yeah. Anyone that didn't stand up, this actually reminds me what a brilliant Australian physicist, John Loki, who's very old now and retired from SARO, but, well, not very old, but he's retired from SARO. But he wrote them, you know when the deep vein thrombosis thing was going on about not moving on aeroplanes and people getting clots and all that sort of stuff. And he wrote to the airline companies, or at least to Qantas, I don't know if anyone else, this is an apocryphal story, it could be completely wrong, suggesting that everyone on board should sing and dance the safety song. And apparently they thought it was serious, and they entered into serious discussions with him about it before they realised. Okay, so let's go. We've got this n log n barrier. We've seen Shannon's reason why we have the n log n barrier. Now let's break the n log n barrier. Woohoo! Let's see how we can break it. Shh, 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 shh. Find the flaw in the chain of logic. Any sorting algorithm must have the ability to have one of n factorial, to sort n things, one of n factorial execution traces. The only way that a program changes an execution trace is through an if, evaluating an if for a while, a Boolean statement. So a comparison of some sort. So there must be at least n log n comparisons in a function, in a sorting function to classify the data. Sounded like a perfect argument, but where was the flaw in it? Yes?
Well, it might not be the flaw, but you said they can only change course when they ask an if statement.
Yes?
It could be randomized.
But how would the randomized thing change? So his suggestion was maybe it could be randomized changing course, but normally that happens through an if statement though. You know, if number is greater than p, or if rand is. How do you actually cause the flow, the control flow to not just split in this binary? It's this annoying binary split, these if statements that's annoying us. You've got to have at least n log n of these binary splits to get there.
You don't have to do those comparisons, there might be other ways.
So, yes, that's right. Yes, yeah. So, but we need more, but that's right. Yeah, maybe we can not do those comparisons, yeah.
If I have a bunch of stuff,
yes,
but I already know where everything in it goes, I don't need to compare it to all the other stuff. I need to just pick it up and then put it where it goes.
Okay, if you have prior knowledge,
Or if I just know where it goes.
if you just know where it goes, you can put it where it goes.
Yeah.
Yes, but so that's right. You're answering a slightly different question to the one I asked, but it's a good answer to that question. And that is how we're going to get to our sorts, our non-comparison based sorts, so that's right. But I was taking a slightly different path to get there. I was just looking at execution flow of a program, the number of different things a program has to be able to do, and noticed it has to be able to do n factorial different things. And the only way we can get programs to do different things is this sort of binary forking we get when they take a choice. Yes?
I'll take another guess.
Have another shot, yep.
One comparison can yield more than two results. Like
One comparison can yield more than two results? How?
Branch out into 3 instead of 2.
In some machine codes it can branch into 3 instead of 2, but in C we only have binary comparisons. So to branch it into 3 with C, we'd actually have to do 2 tests.
I guess it would be n log 3n, which is the same thing.
Yes, if you had 3-way tests, that's right. If you had a 3-way test, it'd be n log n, but to the base 3. That's right. That's a good observation, actually. Can anyone think, you found the flaw, everyone's pecking at the right flaw. It turns out you can get the program to go, it doesn't have to do binary splits. You can get the program in one instruction, in one step, to move to a large number of possible different states. It doesn't have to just go from state A or state B. It doesn't have to do a binary split. One line of program can do more than 2 possible things. using something called, does anyone know? Using arrays. Using what we called indexed addressing. I can say, no, they don't have to be dynamic. No, the dynamism of them, the variable size of them isn't important. It's just that they're an array. Arrays have this lovely property, car x equals 7. This line here, how many ways can this branch? How many different states can we be in after executing this line? Well, as many as there are elements in the array. We could say here x equals 5, and then this line alters 5. Or we can say x equals 10, and this line alters 10. So using indexing, we can execute one command that gives us multiple possible next states. So using this technique, rather than comparing to split between our paths, we used indexing to split between our paths. We can break n log n, using exactly what you said before. The idea being, well, let's look at some ideas. Here's some ideas that people had to do it. One idea was bucket sort. Let's look at bucket sort. Got some buckets. I'm sorting, what am I sorting? I'm sorting...
Tadpoles.
Sorting tadpoles? They go in buckets. All right. I don't know how to put a total order on tadpoles, but oh, the size of, no. I've got to think more about that one. Okay, that could be a good example where I've got to work on it. Let's suppose we're sorting numbers and I'm going to have more. I'm going to sort them into 6 buckets. Maybe these are library books. And they've got a Dewey code, because we use a Dewey classification system in our library. Has anyone ever looked up the Dewey classification system?
Dewey Decimal.
Dewey Decimal? It's completely insane. I looked at it in the library once. It's something like they allocate numbers for different topics. So it's something like, I don't know, all books with a code between 1 and 100 are about philosophy. And all books with a code between 100 and 200 are about, I'm making this up, but it's something like this, religion. And then all books with a code between 200 and 201 are about science. And it's just this weird, you go and look at it in the library, it'll make you laugh. They made a bad estimate of where they're going to have to fit books in the library when they first came up with the code. You know, our library here has a whole floor devoted to books on religion. It's just, you know, it's not a good allocation of indexes to the keys to the thing. Now, this is a nice concept that we might as well explore on. The code on the side of the book is what the book is sorted by, rather than the book being sorted by its title or its author or something like that. What do we call this little code that we sort a whole object by? The key. So that's the key for the object. Up till now, we've been sorting numbers, so every number's been its own key. But let's now suppose we're sorting books, and their keys are their Dewey code. And let's suppose we've got books in the range of 0 to 100. We've got books in the range of 100 to 200. Books in the range of 200. I'm not doing this very well, am I? These seem to be overlapping ranges. That wasn't very clever of me. 200 to 299. 300 to 399. Does anyone know the Dewey system? What is 300 to 399? 499. It's probably books about kings of England. It's fiction. This is not fiction. This is fiction. Okay. What about Harry Potter? They're probably books between 500 and 599. Okay. So I've got a series of books and I'm going to sort them. And I want to sort them by their code. I could use an insertion sort or a quick sort or a bubble sort or something, but instead what I'm going to do is something called a bucket sort. And here's how it goes. I set my buckets out. I pick the book up. I look at its code. Oh, it's in the range 0 to 99. Chuck it in that bucket. Pick up the next book, chuck it in that bucket. Pick up the next book, chuck it in that bucket. Pick up that book, chuck it in that bucket. I use an array indexing operation to work out which bucket to stick it in. I can do that in one calculation or maybe 2. So in one calculation or 2, maybe it's 2 because I have to find that out. It's in a range. Is it greater than this and less than that? Maybe 2 comparisons or maybe 1 multiplication or 1 rounding or something like that. I can place it in one of 6 different locations. So I get a 6-way branch with a constant amount of work. Whereas with insertion sort, to work out what bucket it goes in, you see I'd have to compare the Dewey number with the thing here and think it's not in that bucket, and then I go, it's bigger, and then I suppose I'm trying to stick in 365. I go, 365, is that bigger than the maximum? Yes. Oh, I'll go to the next one. Is that bigger than the maximum? Yes. Is that bigger than the next one? Yes. Is that bigger than the maximum? No. Insert here. That'd be how insertion sort works. Notice it would take 1, 2, 3, 4 comparisons to get it in there. On an average, it'll take n on 2 comparisons, and that's what's going to give us our n squared for insertion sort. But the idea with bucket sort is, if we know about the key and we know the distribution of the key and we store these things in buckets that we can access via arrays, via some form of indexing, I can chuck it straight into the right bucket in one operation. Does that make sense? Okay, that's bucket sort. What do you think of it?
It's very fast.
It looks pretty fast. I've still got to sort within the bucket. Shh. I could sort it, I could put it in the bucket and sort it with another algorithm, or I could recursively bucket sort it, I guess.
You could have 600 buckets.
That's the way we normally go. We have 600 buckets. Then in one operation, I don't have to do comparing with upper and lower bounds or rounding or something. One operation, I can stick it in the right bucket. At the end of this, they're sorted already. And then I can put the buckets together in the order they're in, and it's done. So hopefully this looks a lot like quicksort. Remember, quicksort does a bit of work up front, so that after finishing the quicksort, we can compact everything together, and the joining together happens in constant time, because you know everything on this side of the quicksort occurs before everything on that side. Well, this is like, in a sense, a quicksort dividing it 6 ways. Does that make sense? And we're going to get a constant time merge at the end, and it's just the cost of throwing them into the buckets. It looks pretty neat. Can anyone see a problem with it? Yes?
There's a lot of buckets.
You need a lot of buckets. So if I really looked at the Dewey code system, every book is classified by its Dewey code and 2 letters or something like that. It's got a couple of decimal places. If I needed to have a bucket for every possible book, how many buckets would I need?
Millions.
A lot of buckets. The problem with a bucket sort is either you have to put multiple things in one bucket, and then you've got the problem of sorting that bucket later on. Or if you have one bucket for everything, which at its pure idea is how bucket sort works, then the problem you face is you have an enormous number of buckets. The number of buckets you've got is proportional to the key size, the size of the key. So the complexity of the algorithm is, well, you're going to have to join all the buckets together. How much work do you have to do at the end to join all the buckets together? That's order k, if k is the key size. So you're going to have to do n operations to put them in the buckets, and then k to join all the buckets together. And if k is really big compared to n, oh, you're in trouble. What's another problem that you might think about? What about if we don't try and have one bucket for each thing? We allow multiple things in the bucket that are different, and later on we're going to recursively sort the buckets, perhaps again by some other form of bucket sort. What's the second problem we might have? Yes? What if you get a number that's outside the range? Oh no, I make sure there's a bucket for the whole, that covers the whole key space, all the possible values, but there is a problem, yeah?
If you end up having a lot of stuff already in the bucket sorted, you put a new thing in, there's no or you could have a bucket system within a bucket, I guess. But
Yeah, the problem is you're going to have to sort inside the bucket in some way. Yeah.
if you had a new thing, you'd still want to go all the way through it.
Well, you can put it at the top, maybe. Yeah, he's talking about the problem of actually adding it to a bucket. Could be expensive to add. So if it was a list, you could add it at the beginning of the list. But yeah, there are problems of adding it to the list. Basically, the bucket sort speed up we're getting is that in one operation, we can split things 6 ways, or 10 ways, or 100 ways. Have as many buckets as you possibly can, just so long as the number of buckets isn't so overwhelming that you waste too much time joining all the buckets together at the other end. But the real problem with this is it works really nicely. On average, it runs in linear time if you implement it right. But what's the worst case for this? How could this go wrong? What's the adversary going to do to you when your job is to return the books to the library? They all go in the same bucket. Yeah, someone returns a whole lot of science books. This bucket is more or less empty. This bucket has 99% of the books you're sorting. So if you get collisions, if you get clustering of similar values near each other, then you essentially, instead of having to sort an enormous number and divide it into 6 smaller numbers, you have to sort an enormous number divided into 6 small bits and one still really enormous bit, and you're faced with the original problem over again. So, yeah. But it was a good idea. It was a good idea, and it sort of gives us the hint for how we're going to proceed to get faster and faster. Another good idea is this, something called counting sort. Counting sort is diabolically clever. I'm going to do counting sort on a deck of cards. Okay, I've got a deck of cards. Shh, 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 shh. I'm going to suppose I'm going to ignore suits just because I'm going to make it tractable. So we've got 13 possible values we could have, ace to king, if aces are low. With counting sort, and then we can extend this later on to include suit. There's no drama to do that. With counting sort, I set up an array initially that's as big as the key space. It's like a sequence of buckets. But each bucket is just going to have capacity 1. So I can do it in an array. I don't need some complicated list structure or something else. So I'm just going to set up 13 buckets. Is that 13? And that's ace, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. And I'm going to initialize these to the counts of how many I've seen of each one. And initially I've seen none. And then I'm going to sort my items in 2 passes. The first pass is going to get me some information about the distribution of the items. And then the second pass is going to be able to put them exactly in the right spot using that information. So suppose I've got these are the cards I've got. Ace, king, 3, 7, king, 8. These are the cards I'm sorting. And in practice, it's only going to work, again, if the number of cards is, roughly the same size as the key space, or the same order of magnitude as the key space. If the key space is enormously big, then just initializing this thing with zeros is going to cost me k work, isn't it? The size of the key space, if the key elements in it. So I can't escape, I'm going to have an OK in there somewhere, order k, with k is the size of the key space. Because I'm going to have to initialize it and do stuff with it. So I don't want the key space to be ridiculously big. That's why I just pick ace to king, because that gives us 13, and I'm only going to be sorting something like 10 things, so that's right the right size. Okay, so I wanted to sort these things. What I do is I move one by one through my unsorted list, and I update the count. So I see an ace, I update ace count. Ace count is now 1. Yes?
So is 1.
Oh, I'm going to have a 1 count of 0. This is the special magic card. There you go. That's hopeless. Okay, king, give me your name afterwards. You're in such big trouble. Okay, so king, I update the king. Now, how does the update operation work? Do I say, oh, I've seen a king, so is this a king, is this a king, is this king, is this king? No, how do I update king straight away?
Just go right to the end.
I can jump straight to it, yeah. If king is encoded as 13 or something in my numbering system, I just go counts. Yeah, I've got, an associative array. Well, it depends how associative arrays are implemented. Let's not look at associative arrays. We haven't got them in C. Let's not think about that. Because there's some data structure hiding underneath them, and that's hidden. And depending on how it's done, it has different complexities. But let's just assume it's a normal linear array, like an ordered array, and every card is given a number. So ace is really 1, and king is really 12 or 13. So then I just go counts card plus plus. Can you see? Just in one operation, I instantly update, and I'm in some for loop here, while there's still cards in this pile. Step through them one at a time, and increase counts card. So king goes to 1. What happens next? 3 goes to, the count of 3s goes to 1, the count of 7s goes to, that's everywhere. The count of 7 goes to 1, the count of king goes to 2. That wasn't a very interesting list. 8 goes to 1. I want another double. Let's have another 3. 3 goes to 2. So now I've passed over my data, and I've got an idea of how many occurrences of each possible key value are there. This only works if I know about my keys, just like the last one. The keys need to be in some sort of small, well-ordered, total order, linear range that I understand about. Okay, so if you're doing it by strings, this would be quite difficult, but sorting by a key that's based on numbers where there's a relatively small number, this is going to give me a manageable key space. Now what I do is I'm going to do a pass over this array, and I'm going to work out cumulatively the sum. So the sum so far is 0. The sum so far is 1. The sum so far is 1. The sum so far is 1. The sum so far is 3. 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 4, 5, 5, 5, 5, 5. Does that make sense? And maybe it's another array, or maybe I've just overwritten the last array because I don't need the last array anymore. Now I've got my cumulative positions. Can you see it took how many operations to update the array up here? How much work did I do? Yep, order n to update it. How much to initialize everything at the beginning? Order k. Well, you do if you've got a big key space. The question was, do you worry about your initialization? We've got to notice that there's this k in there. In C, you have to initialize everything. You can't assume things are not initialized.
Once you've thought of initializing, you can just keep it like that, can't you?
Yeah, but I've still done order k work. That's the important thing to notice, because if k was a really big number, like suppose I was sorting 10 things and I had a key space that was a 32-bit integer. I have to do 2 to the 32 bits of work before I can sort those 10 things. You know, I'd be better to just try all permutations one at a time and test them almost. Well, no, but yeah. So if k is really big compared to n, we're in trouble. And then doing this rolling along cumulative sum, how much work is that? That's order k again. I did it along the list. All right, now I've got that's my input list, my unsorted list. I'm now going to create an output list. And I'm going to give them an index value of 0, 1, 2, 3, 4, 5, 6. And here's how I go. It's as simple as anything. I just look up in the array the location of where A goes. So this is exactly what you said before. Put it exactly in the right spot. A, index of A is 0. This goes in location 0. A. Thank you. All right, K. This goes in location 5. Oh, and every time I look up a value, I increase it by 1, by the way. K goes in location 5. And I increase this by 1. What does this now say? 6. 3 goes in location 1. 7 goes in location 3.
Increase 3 first.
Oh, sorry, I didn't increase 3. Thanks. Yeah. 3 goes in location. Sorry, where am I? 3 goes in location. Oh, 7 goes in location 3. Oh, I've got to increase it. Oh, it stays in the same spot. K goes in location 6. I've got to increase it. 8 goes in location 4. I've got to increase it. And 3 goes in location 2. Whew, the output list is sorted. Do you see, in one pass through the data, everything goes into the right spot? Did I write the wrong thing in? Oh, that's meant to be 3. Yeah, except for the small number of human errors I made in implementing that. Can you see how beautiful that is? It's very clever. What's the complexity of this thing?
Depends what K figure now.
It depends it depends on the relationship between K and N. So we're lazy. What we say is O, N plus K. Now it's up to you to make, in a particular case, you'll look at it and say, oh, K's the most significant thing, I can almost ignore N, or N's the most significant thing, I can ignore K, or they're both about the same size. If K is roughly the same order of magnitude as N, you know, it's some linear multiple of N, then that's N plus N, which is N. So yeah, stays in. Okay. Is everyone cool? Can everyone just go, let's just do a play. This was actually, this is called Counting Sort. It was named after the Count in Sesame Street. Can we just give him a hand? Because it's a fantastic sort. He's fantastic. I have one more amazing sort to show you, but maybe short to show you. But maybe we'll talk about something else first, because I did want to talk about exponentiality first. Well, when I say I have one more amazing sort to show you, there are many more amazing sorts still to go. Has anyone did what I suggested last weekend and actually sat down and tried to think of a clever sorting algorithm yourself? You did? You came up with that one? Yeah. You're a very clever man.
You know where all the cards go.
Well done. So you literally came up with counting sort by yourself
We know where they go.
without looking it up somewhere.
Yeah, because you know where they go.
That's fantastic. I'm really pleased, because once someone tells you, you can never invent it for yourself. So he spent that weekend really well, because after today you wouldn't have been. So please spend your time trying to think of how to do them, because as I teach you more and more, not only do all the easy ones start going, but also it sort of channels your mind. It's much easier to think of things when you haven't seen lots of alternatives thrust for you.
I can't believe the car broke down on a rainy night like tonight. I thought tonight was going to be so much fun.
Oh, yes. We are two unbelievably unlucky people.
Yes, and we're going to be two unbelievably wet people if we can't go inside this house and use the phone to call the service station. Oh, and I don't see a doorbell. I guess we'll have to knock.
Yes, the perfect thing to do, to knock. You knock, I will count the knocks. This is turning out to be a fabulously fun evening after all.
Oh, that's what I've learned about you, Count. You always look on the bright side.
Somebody has to.
Oh. You ready?
Yes, I count them always ready to count. 1, 2, 3. That's it? Only 3 knocks?
Oh, I think 3 knocks is enough.
Oh, no. I will knock. 1, 2, 3, 4, 5, 6, 7, 8,
Oh,
9.
That's enough.
No. It's not nearly enough. 11, 12, 13, 14.
There's no one coming to the door.
All the more reason to knock, my dear. 15, 16, 17, 18.
Count, give up.
I'll never give up.